Hey everybody, in this video we're going to get started on chi-squared significance testing. We're going to work through a full example and hopefully get the big ideas that way. So imagine we have this bag of candy. There's 50 pieces of candy in there, and they're all green, red, orange, or purple. And we'd like to test whether all the colors are equally likely as they come off the factory line. So we have this null hypothesis that all the proportions for the different categories are all the same. They're all 1/4. Clearly our data doesn't adhere to that distribution, but that could just be due to random chance. So is it plausible that that's just due to random chance and the null hypothesis is actually true or not? The tool that we have at our disposal here is the Pearson chi-squared test, and we're going to essentially compare the numbers that we got in each of the 4 categories with the numbers that we would expect under the null hypothesis. So let's have a table. So there's the counts for each of the 4 categories as well as the expected counts. 1/4 times 50 is 12.5. It's okay that those aren't integers. These are expected values, not literal pieces of candy. If the null hypothesis is true and all the 4 colors are equally likely, we expect the actual and the expected to be close on average. So let's come up with a test statistic that measures that closeness. We're going to do observed minus expected, and we'll square it so that we don't have pluses or minuses. And we'll weight it according to the size of the particular categories, and we'll add that up across all the different categories. It's just a fact that this distribution for chi-squared is going to be approximately chi-squared of k minus 1, where k is the number of categories. A couple of quick comments on that. First of all, notice we're using the word chi-squared 2 different ways here, both to refer to the test statistic and the name, and it's also meaning the name of the distribution. So the context usually makes it clear which is which. Also notice that k here is the number of categories, not the sample size. That's a common point of confusion. So we compute it, and we get 9.4. And basically, since this is measuring the distance from our data to the expected data, larger values are going to give evidence against the null hypothesis. So we're going to be interested in the probability of getting a chi-squared statistic at least as large as the one we got. The probability that chi-squared is greater than or equal to 9.4 in the distribution chi-squared of 3. We'll set a significance level of alpha equals 0.05 in this problem. So we're going to compute that using the CDF for the chi-squared distribution, so 1 minus that CDF. In R, the code is 1 minus p chi-squared, p CHISQ. The first argument is the critical chi-squared value. The second is the number of degrees of freedom. We get 0.024, and so in this case we're able to reject the null hypothesis. The distribution of candy colors does not appear to be uniform. So before we conclude this video, I want to say just a couple words about the algebra behind this test statistic. It makes sense intuitively. Let's at least do a little math with it. Let's just look at one category. So definitely waving our hands already a bunch. So if n is the sample size and the probability of an observation falling into the first category is p1, then the count y1 for that category is going to be binomial with parameters n and p1. So if n is sufficiently large, and usually 5 is enough, then we have a normal approximation with mean np1 and variance np1 times 1 minus p1. So if we compute a z-score, the distribution is going to, of those z-scores is going to have the standard normal distribution. Notice the numerator of that z-score is actual minus expected, observed minus expected. So the summands for the chi-squared distribution are the squares of these. So let's square this. Let's also remember when we square z-scores, the distribution is going to be chi-squared of 1. So that explains where the chi-squared distribution in our test statistic is coming from. Additionally, if you put your thumb over the 1 minus p1 in the denominator there, then you get observed minus expected squared over expected. So exactly the summand of the chi-squared test statistic up above. Now, we're definitely waving our hands. We only looked at one category and we put our thumb over that 1 minus p1. if you actually do out the arithmetic and look at all the categories, the 2 wrongs actually make a right, and the 1 minus the P1 factor actually goes away. So that's far from a proof, but at least it gives a little bit of algebraic intuition as to why that test statistic makes sense and why it's going to have the chi-square distribution that we claimed it did earlier.